Alright, today we're going to have a look at topic 14 of Introduction to Geometry. We're going to talk about three-dimensional geometry. So far in this course, we have confined ourselves to 0 dimensions, 1 dimension, and 2 dimensions. However, we all know the world around us seems three-dimensional. That in addition to left and right, and forwards and backwards, there's up and down, right? So in this topic, we step off the page and into the real world by considering three-dimensional objects. As we'll see, this isn't much of a step. Much of our work in three-dimensional geometry will consist of reducing problems to two-dimensional situations we already know how to handle. Okay, first of all, let's have a look at the basic concept of planes. So as we mentioned in previous sections, a plane is a flat two-dimensional surface that extends forever. For example, when your book is completely flat, this page is part of a plane. So in this topic, we'll explore planes first, as well as how lines and planes can intersect in space. So the first problem to consider is how many points are needed to determine a unique plane. Well, probably you have already know this, right? The answer is 3. If we only have 2 points, we can find the lines through them, but there are indefinitely many planes that can pass through this line, and therefore pass through our initial 2 points. An example is shown in the figure at right, in which 3 planes are shown passing through the same line. Given 3 or more collinear points, meaning that they are all on the same line, we can still find infinitely many planes that pass through all 3 points. But if we have 3 points that are not collinear, then we have a triangle. The plane of this triangle is the unique plane that passes through the 3 points, as shown here at left. Well, any 3 points are collinear, meaning there is a plane through through all 3 of them. It's easy to find a set of 4 points that are non-coplanar. 3 vertices of a triangle, and a point not in the plane of the triangle will give us an example in which no plane passes through 4 given points. Such a situation is depicted at right, where segment BC is dashed because it's in the back of the figure, right? In other words, we wouldn't be able to see segment BC if this figure were rendered in 3 dimensions. So, in a summary, 3 non-collinear points determine a plane. And now we consider how lines and planes in a space can be related. Okay, so I'll give you some time, probably 4 minutes, to consider these questions first, and after that we'll have a look at the solution together. Okay. Alright, have you finished? Okay, let's have a look at solution together. First question, when two lines intersect, their intersection is a point. When two planes intersect, what kind of figure is their intersection? So we can consider standard rectangular room as shown at right, where EFGH is a floor and ABCD is a ceiling. The walls are portions of a planes. Look at where a wall meets meets the floor, and you'll see an example of two planes intersecting to form a line. Similarly, any two planes that intersect form a line. Well, actually, if we learn the analytic geometry in the later sections, it's very easy to explain this. Okay, second question. Is it possible for two planes to never intersect? Again, let's consider a typical room. The ceiling is a constant distance from the floor. This means that if the ceiling and the floor extended forever in all directions, they would be planes that never intersect. Such planes are called parallel, just as lines in the same plane that never intersect are called parallel. For example, in our figure below, ABCD and EFGH are parallel planes, and we know that parallel planes do not intersect. Okay, next one. Can there be a line and a plane that never intersect? In 3 space, there are 3 possibilities for the intersection of a line and a plane and the related system of equations. Again, when we learn analytical geometry in the later sections, this is very easy to explain. So here, as long as you have an intuitive feeling of the relationship of the lines and planes, that'll be okay so far. Okay, first the line intersects the plane at a point. And second, the line could also lie on the plane, right? And the third relationship is the line could be parallel to the plane. So it is possible that a line and a plane never intersect forever. Okay, next question. Remember that two lines are parallel if they are in the same plane but do not intersect. Can two lines in space be such that they are not parallel but still do not intersect? Well, this is also possible, right? For example, if we consider a typical room, we know lines A, B, and C, G do not intersect and are not in the same plane. Since they are not coplanar, they are not parallel, but they still do not intersect. We call non-coplanar lines that do not intersect skew lines. Are you clear? Okay, next question. Given any two intersecting lines, is there always a plane that contains both lines? The answer is yes. For example, let x be the intersection point of the two lines, y be a different point on one of the lines, and z a different point on the other line. These 3 points determine a plane. Clearly, both xy and line xz are in the plane because xy and xz are. Okay, so in a summary, let's summarize the relationship between lines and planes in 3 space. First, the relationship between two lines in 3 space. Well, there are 4 possibilities for the intersection of the lines. First, the lines are distinct and intersect at a point, which is shown here in the figure at top left. Here, they have a unique point of intersection at this point here. And second, the two lines can be the same line, which means the lines are coincident. Third, the lines are parallel and distinct. This is also possible. In that case, the distance between the two parallel lines is the same anywhere, right? And this distance is the length of the common perpendicular. And last, the distance between the two skew lines. Two skew lines means in 3 space they never touch each other, and they are not parallel. In that case, these two lines are called skew lines. Distance between skew lines can also be found. Distance between the two skew lines is the length of the common perpendicular, which is also the shortest distance between the two lines. Again, when you learn the concept of advanced analytical geometry, it's also possible to find the distance between the two skew lines. So we'll leave this in our future lessons. Okay, and next, the relationship between two planes in 3 space. There are 3 possible geometric models for the intersection of planes. First, if 2 distinct planes intersect, the solution is a set of points that lie on the line of intersection. Second, if the planes are coincident, every point on the plane is a solution, which means the 2 planes are actually the same plane. Third, parallel planes do not intersect, so there is no solution. So if we combine the two equations of the 2 planes, you'll never find a solution. Also, you can verify these situations algebraically by solving linear systems of equations representing the planes. Again, we'll leave this in our future sections, future lessons. Okay, because currently we haven't learned the concept of analytical geometry. Okay, clear? Alright, then next let's consider 2 questions. First, how can we tell if a line is perpendicular to a plane? Can you give an example in the real world of line and plane that are perpendicular? Second, how can we tell if 2 planes are perpendicular? Can you give an example in the real world of 2 planes that are perpendicular? Again, you can use a typical room as an example. Okay, I'll give you some time to consider these 2 questions, and then we'll have a look at the solution together. Okay, now first let's have a look at question A. Suppose line K intersects plane P at point X. If K is perpendicular to every line in plane P that passes through X, then we say that line K is perpendicular to the plane. The line of intersection between two adjacent walls in a typical room is perpendicular to the ceiling and floor of the room. For example, in this figure here, line AE is perpendicular to ABCD. Okay, now let's consider question B. Suppose planes P and Q intersect in line M, and we let O be the point on line M. Consider line J and K in P and Q respectively, such that each of J and K is perpendicular to M at point O. The angle between J and K, which is marked with a theta in the diagram here, is the angle between the planes. We call such an angle between planes a dihedral angle. If this angle is a right angle, then the planes are perpendicular. Again, in a typical room, a wall is perpendicular to the ceiling and to the floor. For example, here plane ABCD is perpendicular to plane BCGF in our room here. Okay, so these are the basic concept of planes. Now let's consider some 3D shapes. First, the concept of prism. By definition, a prism is a polyhedron or solid shape consisting of two identical ends, such as triangle, square, rectangle, and etc. Flat faces or surfaces and uniform cross-section across this length. There are several different types of prisms. First, an oblique prism is a prism in which the joining edges and faces are not perpendicular to the base faces. A right prism is a prism in which the joining edges and faces are perpendicular to the base faces. For example, in the diagram on the right, this is an oblique prism and this is a right prism. This applies if and only if the joining faces are rectangular. If the bases of the prism are in the shape of a regular polygon, then it's called a regular prism. If the bases are in the shape of an irregular polygon, then the prism is called an irregular prism, which is shown here in the diagram at bottom. Regular prism versus irregular prism. So to calculate its volume, the volume of prism, which is usually denoted as letter V, equals the area of the base of the prism times its height or altitude. Surface area is calculated using 2 times its base because it has 2 bases, right? Plus the sum of the areas of all the lateral faces, where A base means area of a polygonal base, and sigma of A lateral face is the sum of the n lateral face, each of which is actually a rectangle, right? And for oblique prism, sometimes the lateral face is not necessarily a rectangle, but a parallelogram. Okay, now let's have a look at some examples of prisms. Note that if a prism has parallelograms at its bases, as well as all its sides, then such a prism is given a special name, parallelopiped. So the figures on the right are typical prisms. So you can have a look at them, and next we'll have a look at some quick quizzes. Okay, also note that the figures on the left are typical examples of prisms, and the figures on the right are not prisms according to the definition. Okay, if you don't have any questions, let's have a look at a quick quiz here. A, B, C, D, E, F, G, H, shown here on the right, is a rectangular prism with AB equals 3, BC equals 4, and AE equals 5. Can you answer each of these questions below? So I'll give you 3 minutes, and after that, we'll have a look at solutions one by one, okay? Alright, let's have a look at solution together. So question A, all of the faces are rectangles. Since AEFB is a rectangle, we have BF equals AE equals 5, right? Similarly, rectangle EFGH tells us that EH equals FG, and rectangle BFGC gives us FG equals BC equals 4. Therefore, EH equals 4. We could also have seen that EH equals BC by noting that both represent distance between parallel faces AFB and DHGC. Again, this is a pretty straightforward question, right? And second question, find the volume of A, B, C, D, E, F, G, H. So we can approach this much as we did finding the area of a rectangle with 1 by 1 squares in section 4.2. We can organize a layer of AB times BC equals 121 by 1 by 1 cubes on face A, B, C, D. This plus 4 more such layers completely fills our prism. So the volume is 3 by 4 by 5, which equals 60. Or we could also directly use a formula to calculate the volume of a prism, which is here. First, we find its area of its base, which is 3 by 4, right? And multiplied by its height, which is 5. Therefore, the volume of this rectangular prism is 3 by 4 by 5. You could use either method, right? Question C. Total surface areas of this rectangular prism is 2 times the area of ABCD, BCGF, and ABFE. So this gives us 94. And question D. Length of AC. AC is the diagonal of rectangle ABCD. Or hypotenuse of triangle ABC, right? So its length is given by the square root of 3 squared plus 4 squared, which equals 5. Also, AC is sometimes called the face diagonal of the prism. Okay, next question. What kind of triangle is triangle ACG? Okay, first let's find triangle ACG by connecting AC and AG. Since CG is perpendicular to the plane ABCD, it's perpendicular to segment AC, right? Therefore, we know triangle ACG must be a right triangle. This is a right angle here. And next, question 5, find the length of AG. From the right triangle ACG, we have AG equals square root of GC square plus AC square, right? We know GC square is 25, AC square is 25, so AG equals 5 square root 2. Also note that AG can be calculated by square root of AB square plus BC square plus GC square. Actually, this is not a coincidence. Segment AG is called the space diagonal of the prism. The lengths AB, AD, and AE are sometimes referred to as the prism's dimensions. So, in a summary, the 3 dimensions of a rectangular prism are commonly called the length, the width, and the height, which is denoted by L, W, and H respectively. For such a prism, we have the following formulas. First, the volume of this prism is given by L times W times H. Surface area is 2 times LW plus WH plus LH. And space diagonal is given by square root of L squared plus W squared plus H squared. Any questions? Okay, if no questions, Next, let's have a look at a special rectangular prism, which is a cube. A cube is a special rectangular prism that has all its dimensions the same. In other words, its base is a square and its height has the same length as side of its base. So suppose we have a cube x, y, z, w, s, t, u, v here. Can you find the formula for the volume of cube with side length s? Then find the formula for the total surface area of a cube with side length s. And then find the formula for the length of segment SY in the diagram, given that the figure is a cube with side length S. So I'll give you 1 minute to consider this question here, and then we'll have a look at solutions together. Alright, have you finished? Okay, first let's consider question A. Since a cube is a rectangular prism, its volume is the product of all three dimensions. We can still use formulas to calculate the volume of a rectangular prism, right? Since all three dimensions are the same, S, the volume of the cube is simply S cubed. The second question, faces of a cube are all squares, right? Therefore, we know each of the 6 faces has area s squared, so the total surface area is 6s squared. Question C, once again we can simply use formulas we already found for a rectangular prism, but to be a little more sporting, let's prove the formula directly for a cube. To find sy, we'd like to create a right triangle that has sy as a side, so we can use Pythagoras theorem here. We draw sy and su, creating right triangles, triangle SUY. We have uy equals s, so all we have to do is to find the segment su. Su is the hypotenuse of triangle STU, so su equals s times square root 2. Therefore, we have length of sy equals square root of su squared plus uy squared, which gives us s times square root 3. Again, you could use either method to find the space diagonal of a cube. So to put this in a summary, we have the following important property for a cube. A cube with side length s has volume equals s cubed, surface area equals 6s squared, and space diagonal equals s times square root 3. Any questions? Okay, if you don't have any questions, let's consider a quick quiz. We consider cube STUVWXYZ. What is the area of SXYV if SV equals 4? Okay, now let's have a look at the solution. First, we start by drawing SXYV so we can figure out what sort of shape it is. Since a segment SV and XY are perpendicular to faces STXW and VUYZ, they are both perpendicular to both SX and YV. So SXYV is a rectangle, right? We already have one side of the rectangle, which is SV equals 4. Therefore, we only need to find SX. Since SX is the diagonal of a square SWXT, we know SX equals 4 square root 2, so area of SXYV equals SV times SX, which is 16 times square root 2, right? Also note that one way to view rectangle SXYV of the previous problem is as the intersection of a plane and the cube, where the plane passes through vertices S, X, Y, and V of the cube. We call such an intersection of a plane and a solid a cross-section of the solid. Many three-dimensional geometry problems are solved by choosing the right cross-section of the problem to consider. Sometimes we even have to consider multiple cross-sections. Okay, if you don't have any questions, let's consider another quick quiz. The right regular hexagonal prism shown has sides of length 4 on base A, B, C, D, E, F and a height of 8 units. Can you answer each of the 4 questions here? Okay, first question. The lateral surface area of the prism. We know each lateral face of the prism is a 4x8 rectangle, right? There are 6 lateral faces, so the lateral surface area is six times 4x8, and this gives us 192, right? Second question, find the total surface area of the prism. To find the total surface area, we must add the area of the two bases to the lateral surface area, which is calculated in question A. Each base is a regular hexagon. Well, if you can recall in previous questions, we actually devised a formula to find the area of a regular hexagon of side length x, right? Actually, we can break it into 6 equilateral triangles with same side lengths. Therefore, the area of each base is given by this formula here, which is 6 times 4 square root 3 over 4, which is 24 square root 3. Of course, this is the area of each of the base. So the total surface area of the prism is given by 192 plus 2 times 24 square root 3, which gives us 192 plus 48 square root 3. Did you get it? Okay, question C. We have already done a hard part. The volume is just the area of a base times the height. So in question C, the volume of the prism is 8 by 24 square root 3, right? Which gives us the volume is 192 times square root 3. You get it? Okay, next question D. Find the length of AB prime, AC prime, and AD prime. First, since segment AB prime is a diagonal of a rectangle ABB prime A prime, we have AB prime equals square root of 4 square plus 8 square. This gives us 4 square root 5. The other two are a little trickier. For AC prime, we consider the cross section ACC prime A prime, and notice that segment AC prime is a diagonal of a rectangle ACC prime A prime. We already know CC prime equals 8, so we only have to find AC. Since triangle ACD is 30, 60, 90 triangle, also make sure you know why, we have AC equals CD times square root 3, which is 4 square root 3. Therefore, we have AC prime equals square root of AC square plus CC prime square, and this gives us 4 square root 7. Okay, last, we're trying to find AD prime. Similarly, AD prime is a diagonal of rectangle ADD prime A prime. To find AD, we recall the dissection of a regular hexagon by its long diagonals into 2 equilateral triangles as shown. So AD equals 2BC, which equals 8. Therefore, we know AD prime equals square root of AD square plus D prime D square, which gives us 8 square root 2, right? Okay, any questions? Okay, so the next important 3D shape we're going to talk about is pyramid. By definition, A pyramid is a polyhedron formed by connecting a polygonal base and a point, called the apex. Each base edge and apex form a triangle, called a lateral face or surface. Again, there are different types of pyramids according to different classifications. First, a right pyramid has its apex directly above the centroid of its base, whereas non-right pyramids are called oblique pyramids. A regular pyramid has regular polygon base. The concept of these pyramids are shown on the right. Well, the volume of pyramid is given by this formula, which is a third of its base times its height. The surface area is given by the area of its base plus the total area of its lateral faces. Are we clear? Okay, now let's have a look at some examples. First, examples of right and oblique pyramids. A right pyramid is a pyramid whose apex is exactly over the middle of its base. The perpendicular line from the apex to its base center is the height. Oblique pyramid is a pyramid whose apex is not exactly over the middle of its base. The perpendicular line from the apex to the base is the height. Can you see the difference? Okay, next, the difference between regular and irregular pyramids. Regular pyramid is such a pyramid whose base is a regular polygon. For example, equilateral triangle, square, or regular pentagon, which means all sides are equal. All its lateral faces are the same. Irregular pyramid is a pyramid whose base is an irregular polygon, which means sides are not necessarily equal to each other. Its lateral faces could be different. Okay, next, examples of pyramids according to the number of sides of its base. We could have triangular pyramid, square pyramid, rectangular pyramid, pentagonal pyramid, hexagonal pyramid. Usually a pyramid with n-sided bases has n plus 1 faces, n plus 1 vertices, and 2n edges. For example, a triangular pyramid has 4 faces, consisting of 1 triangular base and 3 triangular lateral face, and 4 vertices and 6 edges. This is a very useful pattern you should remember. Okay, next let's consider some quick quiz. ABCDE is a square right pyramid such that BC equals 6 and AC equals 5. Could you find the total surface area and volume of that pyramid? Have you finished? Okay, first, you can find the area of the base quickly. BC squared equals 36, right? The base is very easy, but to find the area of the triangular faces, we'll need the altitude of one of its faces. We start by drawing AO, the altitude of the pyramid. Because the pyramid is right, O is the center of base BCDE. We suspect that each triangular face is isosceles because the pyramid is right. We can prove this by noting that since AO is perpendicular to the base, it's perpendicular to both OC and OD. We have OC equals OD because O is the center of the square. So triangle AOC is congruent to triangle AOD by SAS congruence. This triangle congruence gives us AC equals AD. Therefore, triangle ACD is isosceles, so the median from A to CD is also an altitude. Since AC equals 5 and CM equals CD over 2, which is 3, we have AM equals 4 from right triangle AMC. Therefore, we have the area of ACD equals AM times CD over 2, which is 12. Then our total surface area consists of 4 of these triangles plus a square, which is 4 by 12 plus 36, which is 84. Turning to the volume, we need the height of the pyramid AO. We can build a right triangle but by connecting O to either M or to one of the base vertices. In the diagram, we have right triangle AOM. Since OM equals BC over 2, which is 3, and AM equals 4, we have AO equals square root of AM squared minus OM squared, which is square root 7. Since the area of this base is 36, we know the volume of the period is 36 times square root 7 over 3, which gives us 12 square root 7. Once again, we built right triangles to find the length we needed. So as we saw in this problem, finding the lateral surface area of a regular right pyramid is easy once we know the slant height and the side length. We can even build a formula for it. Okay, if you don't have any questions, let's consider another quiz. Can you find the formula for the lateral face area of a right pyramid whose base is a regular n-gon with side length S and whose length height is L? Okay, let's have a look at solution together. Each of the lateral faces of the pyramid is a triangle with height L and base S. Hence, each of these triangles has area SL over 2, right? There's one triangle for each side of this base, so there are n triangles which have a total area of n times SL over 2, or NSL over 2. Note that NS equals the perimeter of the base, so the lateral face area of a regular pyramid is half the product of the slant height and the perimeter of the base. You can also use this as an important property to solve questions. Okay, consider another question here. A triangular pyramid is more commonly called a tetrahedron. A regular tetrahedron is a tetrahedron whose edges all have the same length. You can find the volume of a regular tetrahedron that has sides of length of 6. Okay, next let's have a look at solution. To find the volume, we need an altitude, right? So we can draw altitude AG from A to triangle BCD. Since AG is perpendicular to plane BCD, triangles AGB and triangles AGC and triangles AGD are all right triangles. Because AB equals AC equals AD and AG is obviously the same in all three triangles. We have triangle AGB is congruent to triangle AGC, which is congruent to triangle AGB by HL congruence. Therefore, we have BG equals CG equals DG, which means that G is the circumcenter of triangle BCD because it's equidistant from the vertices of BCD. Since triangle BCD is a equilateral triangle, G is also the centroid of triangle BCD. We can build more right triangles by connecting BG to M. Since triangle BCD is equilateral, BM is a median and altitude. Therefore, DM equals DC over 2 equals 3 and BM equals 3 square root 3. Since the centroid of a triangle divides its median in a 2-to-1 ratio, we have BG equals 3 over 2 over 3 BM, which is 2 square root 3. And finally, we can find AG from right triangle AGB. AG equals 2 square root 6. Since the area of triangle BCD is DC times BM over 2 equals 9 square root 3, our volume is the area of triangle BCD times AG over 3, which equals 18 times square root 2. Similarly, we can show that the volume of a regular tetrahedron with edge length s is s cubed square root 2 over 12. Okay, next, the concept of regular polyhedron. These 5 regular polyhedrons are collectively named the Platonic solids after the great Greek philosopher Plato. A regular polyhedron is a convex polyhedron in which all the faces are congruent regular polygons, and there are the same number of edges. The most typical regular polyhedron we see is the cube, right, which has 6 faces, 12 edges, and 8 vertices. If we have 4 faces, then we have a tetrahedron, which has 6 edges, 4 vertices. Also, we could have octahedron, which has 8 faces, 12 edges, and 6 vertices. The decahedron, which has 12 faces, 30 edges, 20 vertices. Or icosahedron, which has 20 faces, 30 edges, and 12 vertices. Okay, next let's consider example related to regular polyhedron. ABCDF shown here is a regular octahedron with AB equals 4. Can you answer each of the following questions? Okay, let's have a look at solution together. First, since BCDE is a square, BD equals BC times square root 2, right? all of the sides of a regular polyhedron have the same length, so BC equals AB equals 4 and BD equals 4 square root 2. Second, instead of thinking of octahedron as a square pyramid, ABCDE and FBCDE glued together, we can think of it as BAEFC and DAEFC glued together. Therefore, ACFE is also a square, so AF equals BD, which equals 4 square root 2. Of course, we can also just note that since the polyhedron is irregular, distance between directly opposite vertices must be the same no matter which pair of opposite vertices we choose, right? Third question, BCD is a square with side length 4, so its area is 4 square, which is 16. Last, to find the volume of the regular octahedron, we think of it as two congruent square pyramids, ABCDE and FBCDE. Since altitudes from A and from F, respectively, of these two pyramids together make up AF, the height of each pyramid is AF over 2, which is 2 square root 2. The area of a base is 4 square, which is 16, so the volume of each pyramid is given by 16 times 2 square root 2 over 3. And this gives us 32 square root 2 over 3, right? Therefore, our octahedron has volume twice of that value, which is 64 square root 2 over 3. Did you get it? Okay, last, let's have a look at an important formula which is called Euler's formula, which states that for any polyhedron that doesn't intersect itself, the number of faces plus the number of vertices or corner points minus the number of edges always equals 2. Well, this is usually written as the following formula here. F plus V minus E equals 2. For example, we can try with the 5 platonic solids. If we verify F plus V minus E, you will find each of them will have the value 2. Again, here I'm not going to give you a rigorous proof here, but just briefly explain why. So imagine taking the cube and adding an edge from corner to corner of one face. Then we get an extra edge, right? Plus an extra face. Therefore, we have 7, which is number of faces, plus the new number of vertices, which is 8. Original, the same way as original, minus the new number of edges, now becomes 13, right? Again, F plus V minus E is still 2. And then you can try to include another vertex, and still we could get an extra edge. And if you verify F plus V minus E, you still get the value 2 here. No matter what we do, we always end up with 2. So remember, this is an important formula. F plus V minus E always equal 2 for any polyhedron that does not intersect itself. Okay, for example, if I tell you a solid has 13 vertices and 24 edges, given that Euler's formula applies to this solid, then how many faces does it have? So immediately you should know the answer is 13, right? Because Euler's formula tells us that F plus V minus E equals 2. So here we have 13 vertices, 24 edges. Of course, we have f equals 26 minus 13, which is 13, right? Okay, so that completes topic 14. Three-dimensional geometry. And next, let's have a look at topic 15, curved surfaces. Okay, topic 15, curved surfaces. In this topic, first we'll talk about the concept of cylinders. By definition, a cylinder is a three-dimensional solid that holds two parallel bases joined by a curved surface at a fixed distance. These bases are normally circular in shape, like a circle, and the center of the two bases are joined by a line segment, which is called the axis. The perpendicular distance between the two bases is called the height, denoted by h, and the distance from the axis to the outer surface is the radius r of the cylinder. Of course, we have different types of cylinders. For example, a right cylinder is a cylinder that has closed circular surface having two parallel bases on both the ends and whose elements are perpendicular to its base. Non-right cylinders are called oblique cylinders. The volume of a cylinder is given by this formula: V equals pi r squared h. V is the volume, r is the radius, h is its height. Surface area is given by 2 pi r squared, that's the total area of the two bases, plus 2 pi r h. 2 pi r h is the area of its lateral face. Again, r is the radius and h is the height. Are you clear? Okay, let's consider an example here. The figure shows a right circular cylinder, also known as a cylinder, with radius 3 and height 5. Can you answer each of the following questions? Okay, let's have a look at the solution together. First question. The area of the base is pi 3 squared, right? So the volume is given by pi r squared h, which is pi times 3 squared times 5, and this gives us 45 pi. Second question, what is the lateral surface area of our calendar? So this is given by 2 pi rh, right? And that's 2 times pi times 3 times 5, which is 30 pi. Next, total surface area consists of the lateral surface and two bases, which is 2 pi r squared plus 2 pi rh, and this gives us 2 times pi times 9 plus 30 pi, and this gives us 48 pi. Last, find the formulas for the volume, lateral surface area, and total surface area of cylinder with radius r and height. Okay, we already know the formula for the volume is given by pi r squared h, right? Lateral surface is given by 2 pi rh. Total surface is given by 2 pi r squared plus the lateral face, which is 2 pi rh, right? Okay, next let's have a look at another example. The radius of a cylinder is 2/3 of its height. Can you find total surface area of cylinder if its volume is 96 pi? Okay, let's have a look at solution together. We could let the height be h, and so the radius is r equals 2/3 its height, which is 2/3 h. Since the volume is 96 pi, we have pi r square h equals 96 pi, right? Substituting for r gives us 2h over 3 square h pi equals 96 pi. Of course, we can solve this equation for h, which means h equals 6. Therefore, r equals 2h over 3, which is 4. Now we can find our total surface area, which is 2 pi rh plus 2 pi r squared. And this gives us 48 pi plus 32 pi, which gives us 80 pi in total. Any questions? Okay, next let's have a look at the concept of cones. By definition, a cone is a 3D solid geometric shape having a circular base and a pointed edge at the top called apex. A cone has one face and a vertex. There are no edges for a cone. If the axis of the cone passes through the center of the base at right angles to its plane, then the cone is a right cone. Otherwise, it's called an oblique cone. The volume of a cone is given by this formula. B equals a third pi r squared h. Surface area is given by S equals pi r squared plus pi rl. where L is the square root of r squared plus h squared. R is the radius, h is the height, L is the lateral height or slant height. So the concept of slant height is illustrated on the diagram on the right. So please have a look at the concept here. Any questions, just let me know, okay? And next we'll have a look at some typical examples that related to cones. Alright, next let's have a look at a very straightforward question here. Can you find the volume of a right circular cone that has radius 6 and slant height 8? So basically we need the height in order to find its volume, right? As we did with the pyramid, we can build a right triangle to find its height. We can draw A, O, the axis of the cone, and connect A and O to B. A point on the circumference of the base. Since OB is the radius and AB is the slant height, we have AB equals 8, OB equals 6. Since the cone is right, angle AOB is a right angle, so according to Pythagorean theorem, we have AO equals 2 square root 7. Therefore, we have the volume of the cone equals a third of pi r square h, which is given by a third of pi times 36 times 2 square root 7. And this gives us 24 pi square root 7. You get it? Okay, another question. A semicircle is rolled up to form a cone as shown here. If the radius of the semicircle is 8, what is the volume of that cone? Okay, so here we need to find both the radius and height of the cone, right? At first, it seems that all we are given is the slant height. However, the information about the uncontrolled curved surface can be used to find the radius in a couple of different ways. For example, we can roll it up. When we roll up the semicircle into a cone, the arc BCB prime becomes the circumference of the base of the cone. Since this arc of the semicircle is half the circumference of a circle with radius 8, its length is 8 pi, right? And if we let the radius of the base of the cone be r, then we have 2 pi r equals 8 pi. Of course, this will give us r equals 4, right? And we know the slant height AB is actually AB prime, which is 8, and then we can easily find its height, which is square root of 64 minus 16, which is square root of 48, and that is 4 square root 3. Then the volume is 1/3 of pi r squared h, which is 1/3 times pi times r squared, which is 16, times h, which is 4 square root 3. So this gives us 64 pi square root 3 over 3. You get it? Okay, if no questions, another important 3D shape is called sphere. By definition, a sphere is a set of points that all at the same distance r from a given point in 3D space. That given point is the center of the sphere, and r is the sphere's radius. For example, basketball can be abstracted into a shape of a sphere, right? The volume of a sphere is given by V equals 4/3 pi r cubed. Surface area is given by S equals 4 pi r squared, where the only parameter here is r, which is the radius of that sphere. For example, let's consider a quick quiz. The volume of a square is numerically equal to twice its surface area. What is the radius of that sphere? So in that case, we could let the radius of the sphere be r. Then we have volume equals twice of the surface area in number, not in units. Of course, we have different units, right? Then we have 4 pi r cubed over 3 equals 2 times the surface area, 4 pi r squared. And we could easily solve r, right? First of all, we could cancel a r squared to both sides. This will give us, okay, also cancel a pi. This will give us 4 r equals 2 by 4 by 3. Of course, here r equals 6, right? Okay, next, let's use an example to illustrate one important property of a sphere. Can you prove that if a plane passes through the interior of a sphere, then the intersection of the plane and the sphere is a circle? Okay, first let's draw a diagram to illustrate situations. Suppose we have a sphere here. Then we have a another plane that intersect with the sphere. That's the center of the sphere, O. Center of the circle. Oh, sorry. Well, draw a perpendicular line, OX, that is perpendicular to that plane. Connect X and a point on the sphere. So we could let O be the center of our sphere, R be its radius, and P be our plane. We let X be the foot of perpendicular segment from O to plane P. X is a point we think is the center of our circle. Let A be a point where surface of the sphere meets plane P. Since triangle OXA is a right triangle, we have XA equals square root of OA squared subtracted by OX squared. OA is just radius of that sphere, so we have XA equals R squared minus OX squared. Similarly, every point where surface of the sphere meets plane P is the same distance R squared minus OX squared, right? From X. Hence, the intersection of the plane and the sphere is a circle in plane P, with center X and radius square root of R squared minus OX squared. Furthermore, every point in plane P that is on the circle with center X and radius XA is on the sphere. And then we have proved two very useful facts about cross-sections of a sphere. Every cross-section of a sphere is a circle, or a point, where the cross-section plane is tangent to the sphere. The segment connecting the center of the sphere to its center of its circle is perpendicular to the plane of the cross-section. A cross-section of a sphere that has the center of the sphere as its center is sometimes called a great circle of the sphere. Okay, clear? Okay, now let's consider an example question. A plane cuts through a 26 centimeter diameter sphere, but the closest it gets to the center is 5 centimeters. What is the area of the intersection of the sphere and the plane? Okay, again, we can draw a diagram to illustrate the situation here. So in this problem, we are simply considering a specific cross-section of a specific sphere is so close to the previous question that we can even use the same diagram, right? The diagram is basically the same. We are given that AO equals 26 over 2, which is 13, and OX equals 5. Then we can easily find the length of XA from triangle AXO by using Pythagorean theorem. Of course, this is 12, right? We know that this cross-section is a circle, so its area is just a pi r squared. And of course, that's pi times 12 squared, which gives us 144 pi. And do not forget the unit is square centimeters. So this is our final solution. Any questions? Okay, if you don't have any questions, let's have a look at some more questions. The ant is now on point A of the cylinder shown here. He wishes to walk along the curved surface of the cylinder to point B, where BC is the height of the cylinder and C is on the top base, such that AC is the diameter as shown. given that cylinder has height 4 and radius 3, what is the length of the shortest path atom can take? Okay, have you finished? Well, in this question, actually we can unroll the cylinder, right? If we unroll the cylinder, we see that we can actually get a rectangle. So this is your point C, this is your point B, this is your point A, right? So the task is to get B from point A. So BC still equals the height of the cylinder, so we have BC equals 4. However, here AC is not the diameter of the original cylinder, but rather the distance from A to C along the circumference of the base. Therefore, AC is half the circumference of the base of a cylinder, which is actually 3 pi, right? Make sure you see that. From the right triangle ABC, we can now find the distance AB equals square root of AC squared plus BC squared. And this gives us square root of 16 plus 9 pi squared. Did you get it? Also note that this is not the distance from A to B in space in our original cylinder. This is a length from A to B along the curved surface to the cylinder. Also note that if the ant is willing to walk across a base of the cylinder, there is a shorter path he can take. Okay, now let's consider another problem which is more complex. A ball with radius 6 inches is tangent to the wall and the floor in my house. Given that the wall is perpendicular to the floor, what is the radius of the largest ball I can slide into the space between the ball and the corner where the wall meets the floor? Okay, so here we have a 3D problem involving spheres that are tangent to each other and to some planes. So we consider a cross-section including the centers of the spheres and points of tangency. Hopefully this allows us to build helpful right triangles. So first let's draw the diagram to illustrate the situation here. We have a larger ball. Okay, let's use some tools here. A larger ball. And then we have a smaller ball. So this is a wall. This is our floor. So this is center of the larger ball, center of the smaller ball. O and P are the centers of our spheres, which are tangent at point X. These spheres are tangent to the floor at point M and point N. Sphere always tangent to the wall at point L. Since the spheres are tangent to the wall and floor, O and P are equidistant from both. Therefore, both O and P are on the angle bisector of LCM. Sorry, let me correct this a little bit. Okay, both O and P are on the angle bisector of angle LCM. Since LCM equals 90 degrees, we have angle OCM equals angle PCN, which is 45 degrees, right? So triangle OCM is an isosceles right triangle. Similarly, triangle PCN is also an isosceles right triangle. So we have PC equals PN square root 2, which gives us 6 square root 2, and XC equals PC minus PX, which is 6 square root 2 minus 6. If you let the radius of our smallest sphere be R, we know that OC equals XC minus R, which is 6 square root 2 minus 6 minus R. However, from triangle OCM, we also have OC equals OM square root 2, which equals R square root 2. Therefore, we have two expressions for OC, which we can set equal. So we have R square root 2 equals 6 square root 2 minus 6 minus R. And this can solve R, which equals 6 square root 2 minus 6 over 1 plus square root 2. We can realize that the denominator, we can rationalize the denominator by multiplying the top and bottom of the fraction. So rationalize R will give us this number here times 1 minus square root 2, 1 minus square root 2. And eventually we have R equals 18 minus 12 square root 2. So this is a radius of the largest possible ball I can slide into the space between the ball and the corner where the wall meets the floor. Okay, so this is pretty much about it, and that completes topic 15, curved surfaces. And before you leave, I'll give you today's homework. Please try as much as possible, okay? Alright, I'll see you next time. Bye.